Hi, welcome back for the tutorial, which is about statistical inference. So the question, how do we draw actual conclusions in a scientific sense from the differences and similarities between models? To do that is often represented in graphs like this in papers, where we compare the different models to some brain area, for example, and then want to conclude that in this case, model L3, whatever that might mean, is the most aligned one, the most similar one to the brain area we were measuring. And to actually do this as a scientific conclusion, we should run statistical inference, right? So we should not just say the bar is highest, but we should actually find out what our uncertainties, so these error bars about the model evaluations are, and run proper statistical tests to compare them. And to understand where those tests come from, the first step is to understand why we are uncertain about those model evaluations in the first place. And there are two reasons for this, which are stimuli and subjects, which both influence the results of our model comparisons. The first one is just if we use different stimuli, we will get different results, right? We've seen this throughout the tutorials, and whether it's comparing different deep neural networks or different brains to each other, if we use other stimuli, we will get different results. This seems kind of natural and applies to both applications. In neuroscience, it's also very intuitive that there will be different results if you run this for different humans or subjects, as different people have slightly different brains, and there will be measurement error and like different configurations in the brain and all kinds of that. And this will result in some variation of the results, and we want to generalize to the general population of subjects. In today's AI research, a very similar thing actually happens for artificial neural networks too, which we call nuisance variation. So if you just train the same neural network, allegedly, with a new weight initialization or a different order of the stimuli in training, or different learning rates, or a different optimizer, or many other small choices you have when training those neural networks, you'll get slightly different neural networks, and they will result in different model comparison results or representational comparison results. And thus, we should also in AI take this into account and look at this variation to draw our conclusions and make sure that we're not relying on a fluke. In both of those cases, the normal rules for statistical inference apply. So statistical inference assumes that the things you measured are a random draw from a bigger population, and that you want to draw conclusions about this bigger population, which in turn means that you need to measure things about the stuff you want to generalize to, right? This is especially important for the stimuli, where we've seen that you might get completely different results for natural images than you get for adversarial examples. So as a consequence, if you want to generalize to both, you would have to measure from both, right? But assuming that we have measured random samples from the things we are actually interested in, how do we actually get the statistical inference to run? Here we propose bootstrapping as the general solution. So bootstrapping means that we draw new resamples from the data that we've actually collected. And if we have large enough data and do this resampling often enough, we will get an estimate of the variability across real repeats of the complete experiment from those resamplings of the data that we actually have. For our representational similarity analysis, this would look like this. So the data measured there is the RDMs, the representational similarity matrices for the different subjects. And each of those have like the different stimuli along both of their axes. And then we can draw like resample the stimuli or resample the subjects to generate uncertainty estimates. As I said, this is called a bootstrap. And depending on what thing we resample, we can control what we want to generalize to, right? So if we only resample the subjects, we will only generalize to new subjects. If we resample only the stimuli, we will only generalize to new stimuli. So, and this is what you will be doing in this tutorial. I just want to now show you that this does indeed work. So let's have a look at this. This is data from a recent paper I published and with some colleagues, where we did large number of simulations, always comparing the standard deviation we estimate from bootstrapping and dividing this by the true standard deviation that we get by actually rerunning the simulation and creating new data sets from this. And what you then can see here, right, like we would love to be at this 1.0 line, which would mean that our bootstrap exactly estimates the variance correctly. And indeed, if we have sampled enough conditions or stimuli, we converge to values close to 1. So we get this estimation right fairly well. And the same is true if we just bootstrap the subjects. Unfortunately, there's one more hurdle, which is that if you do both, so if you want to generalize to new stimuli and new subjects, and do this in the naive way, we are fairly far off. So then we overestimate the uncertainty by running the bootstrap, which is not good because it, of course, loses substantial power, right? So the factor like 1.4 here would be a factor 2, and variance would be roughly mean you have to collect twice as much data to draw the same conclusions. So what is wrong with this two-factor bootstrap? Well, we overestimate the variance. That's what we want to fix. And the problem here is that each of the bootstraps along the dimensions already contains the noise variance. You might be familiar with this if you've used the bootstrap before. If you just want to generalize to new subjects, let's say, which is a common thing, then you wouldn't have to include anything special to have the noise variance included. Overall, this leads to a triple counting of the noise variance, because in this two-factor case, you get this noise variance included in the variance that you have for the subject, the variance you have for the stimuli, and the variance that you have for the interaction. So more formally, this looks like this. We can split up the variance for our estimates into one which is due to the subjects, one that is due to the stimuli, here y, and an interaction or like measurement noise term. So any kind of variance that is not explained by either of the two. And if we do all the boring math, which is just rearranging squares, yeah, it's a relatively simple math, you can actually derive what the actual bootstrap variance is. And it turns out to have like n minus 1 over n factors for these two, which is almost right, but unfortunately has 3 of those additions for the xy interaction. So like it is actually pretty close to just a factor 3 off for this particular variance component. To fix this, we can just calculate a correction, right? So now that we know a formula for how far off we are, we can add the bootstrap just along each of the dimensions, which then gives us 3 equations for 3 unknowns, and we can solve this for the variance. And with that correction, the bootstrap actually works pretty well, and we get back to values very close to 1. This is essentially as good as just bootstrapping the stimuli was in the previous slide. So I hope I convinced you that these bootstrapping methods with the corrections actually work correctly. And to make this easier for you to do, we actually provide a toolbox for representational similarity analysis, which does all this resampling. And we hope you'll find it helpful, as this tutorial is based on you using this. And what you'll be concretely doing is that you get a part of this natural scene dataset, which is a very nice 7 Tesla fMRI dataset about brain measurements. And you'll be comparing representations from deep neural networks against this part of NSD. And then run through all the different possibilities for inference here to learn how those work and what kind of results you can expect from them. And with that, yeah, have fun with the tutorial, and I hope in general you found this helpful. And yeah, all the best. See you soon.